So here's my notebook. And I started the same way we started last time. I defined our equations, and I wanted us to solve these equations numerically. So let me just tell you what these equations are. So I defined an equation, EQ. I'm going to kill my kernel just in case I have anything left over. I have equation U, which was the derivative of U with respect to time is equal to 1 minus U of t. This is something that I saw in most people's notebooks when I jumped on breakout rooms last time. U as a function of t is the variable. So if you type in, instead of this, you type in this, that's a different variable. Mathematica treats U as a different variable than U of t. So anytime you have U and anytime you have Q, it has to be U of t, Q of t. U prime of t, Q prime of t. So this is the variable that needs to be in your equations and your initial conditions. So that was a mistake I saw most people having as they were defining things. So this is the equation. It was 1 minus U of t times the exponential of epsilon times parentheses Q of t minus 1. U is our concentration. T is our dimensionless temperature. Everything here is dimensionless. Epsilon is our small parameter. It has the initial condition for U that U at time 0 is equal to 0. And similarly, our equation for Q is the first order derivative of Q, which is equal to, and again, look, I want to point out because it's really hard to see, this is a single equal sign. This is a double equal sign. When you hit a space, it makes it look like that. So our equation for Q looks like U of t times the exponential of epsilon times Q of t minus 1. And then we have an additional term here, which is minus Q of t. I want to point out this is also something that I saw in a couple of different breakout rooms when I jumped in here. These are systems of equations. They cannot be solved independently. This is kind of like having something like 3x plus 2y equals 1 and 5x minus 3y equals 7. You can't solve for x and y without solving these two equations simultaneously. So as we go forward, we need to think of these as the 4 equations that we will be solving simultaneously. To Mathematica, it doesn't care that some are governing equations and some are initial conditions. It just wants you to send it a list of equations, equation 1, 2, 3, and 4. And so to get an idea of what we're doing, we're going to solve this equation numerically. So if you recall, to solve this equation numerically, first let me run these. To solve this equation numerically, we use ND-solve. And then we send it a list. So it's going to look like ND-solve. And we send it a list of equations. So that's going to be the 4 equations. 1, 2, 3, 4. And then we send it. In this case, the difference here is that we're not solving for one dependent variable. We're solving for 2 dependent variables. So again, you need to send it a list for those 2 dependent variables for our one independent variable over some domain. So I just chose the domain because I know this problem. 3 from 0 to 10. If you're in practice, you're going to do this either because you know what time is reasonable, or you're going to just pick something and solve it a few different times until you find the right dynamics that you're looking for. So this is like the syntax. So here I have ND-solve of equation U. I picked epsilon to be about 0.5 just to kind of highlight the nonlinearity here. So for both EQU and EQQ, I send it, replace epsilon with 0.5. I give it the other 2 initial conditions. I tell it to solve for U and Q for t from 0 to 10. And so I save that as my variable solve. And then I can plot this numerically, and remember for numerical plots, because of the strange way it gives you a solution, you have to evaluate Q and replace it with Sol, and evaluate U and replace it with Sol. If you're curious about this, we can chat about it, but it's just think of this as kind of a quirk that to remember. You'll know it. You'll know you need it if you just try to plot Q of T with Sol and nothing happens. So you can kind of go back here. I made this plot transparent, so I made these curves a little transparent here. And that'll make it so that I can show you how our approximate solution is behaving at each order of epsilon that we solve for. So all the rest of this is just styling the plot, putting labels on there, giving a range. The blue curve is the first, so blue is always the first curve unless you tell it a different color. So that means the blue curve is our Q, and the orangish curve is our solution for U. So already, before we even start working on the solution, we can start to see the differences between this problem and the last problem. The last problem, one of the fundamental things we were curious about was what happens at long time. So the question was, you throw the ball up, it's going to spend some amount of time in the air, and it's going to come back down. We were curious about when it would come back down. We didn't know when it would come back down, so we ended up coming up with a really elaborate way to determine when that ball would come back down. Here, the nature of the problem is different. Our equations have exponentials in them, and exponentials that at long times, this means that the quantity in this equation, these things are going to go away, and these things are going to fall to a value of 1 on the y-axis. So what I mean by that is, as I change epsilon, what changes is not the, if you remember in the last problem, as I changed epsilon, the amount of time, the parabola kind of stretched out along the x-axis until the point where it stopped stretching on the x-axis. And that point at which, you know, the projectile left Earth's gravitational field, that kind of was the really significant nonlinearity in the problem here. Here the nonlinearity is different. Nonlinearity is actually occurring kind of in this intermediate regime. It's not really happening at small time, it's not really happening at large time, it's kind of happening in here. And you can see that as I change epsilon. So if I take epsilon as 0.01, and I plot this again, I see that this thing, our solution at the edges, doesn't really change. Starts at 0, rises fast, eventually plateaus. If I change this thing to about 1, oops, I lost the plot. So let's go up to it. You can start to see that what we're seeing are these kind of damped oscillations of our solution. This problem is kind of like if you tell your oven to heat up to 400 degrees, what your oven is going to do is it's going to jack up the temperature up to like 425 and then realize it went too far and then go back down to 375 and then come back up to 405 and then kind of decay until it gets to the temperature that you set it at. And then, you know, this is kind of our control parameter, which is kind of controlling the damping of this solution. So I'm going to go back to this kind of small-ish parameter for epsilon. It's not that small, but it's definitely smaller than 1. But the point I want to make is that what's the interesting thing happening here is not happening at the ends, it's happening in the middle of our solution here. So we're going to capture the beginning dynamics and the end dynamics, even at order 1. But it's all that nonlinearity and those oscillations in the middle that we're going to miss. So again, I'm just kind of trying to use the visualization tools here to help us kind of understand what we're trying to solve for. Is anyone having trouble getting this plot on their computer? All right.
Getting an error on the ND solved. This was the equation. I was expecting a list of equations, but I haven't defined. It's just something I can solve.
Okay. If it's expecting a list, it needs to be in those curly braces. Yeah, another question.
So I noticed that we generally have two different ways of defining our equations.
Yeah.
One way will be an equals and then a double equals.
Yeah.
And then one way will be like a U underscore, that whole thing with the colon equals, I think, if you want to. Why one way or the other, or?
Totally, yeah, it's a great question, and again, this kind of goes back to the question that I think Jacob asked last class, which was, why do we have two versions of the projectile problem? And I'm kind of trying to, what I don't want to do is to say, like, this is the only way to solve these problems. And so I'm kind of showing you the different ways you can solve these problems. Some of them might be more intuitive to you than others. And some of the ways that you insert solutions and replace your variables might be more intuitive and easy for you to see. I did this one a little different to give you another kind of way that you can approach it. Using Mathematica, just like using MATLAB, is very much actually coding. Like, you are coding here. There's 20 different ways to solve kind of any algorithmic problem. I'm kind of trying to show you the different ways so that way you can feel like it's not a set of rules you have to follow. I want you to be thinking about what you're doing and then do what makes sense to you. And then eventually you're going to be like, I wish this looked like that, or I have a hard time seeing that. And you'll kind of find the way that works for you. So I'm just kind of showing you different ways here. Each of the ways that I'm introducing this have their advantages and disadvantages depending on like what you're trying to do. So for instance, when you're like using my function of u, which is a function of t, that's really robust, and you can very simply replace different functions in there and use the same code. Oftentimes you're solving like one particular problem, so you don't maybe need that flexibility that comes with like messier code. And so this is another example to kind of show you like, all right, let's just dive in. We know we're solving this equation. Let's see what it looks like. But it's a good question. So. Okay. I also saw a lot of people defining those expansions that we use, that expansion general, a bunch of different ways. I wanted to show you, maybe this will be annoying, or maybe this will be like, oh, that's kind of powerful. I redefined expansion general here, and I did it in a way that hopefully will make it easier for us to use. I just said, instead of calling it, so expansion general used to look like this. And all I did was I said, well, if we replace x here with some temporary placeholder, I'll call it bar for my variable, and I just add that as part of the function that I send to expansion general, then look what I can do. I can immediately use the same function to generate my expansion for my two variables. If you're solving a system of equation with, n different variables, then it's going to be really annoying if you have to define n different functions that all basically do the same thing. So here's a really simple way where you can have our expansion and you just tell it, I want to call this one with u, call this one with q. And oops, where did that go? Yeah, there we go. And so all we had to do is kind of change our definition a little bit, and then we have a really powerful way of using this. And I just, again, used notation, and I made these subscripts symbols. This notation has that little annoying caret there at the end. That's the one next to the 1. You can copy that from our other notebook if you want. Questions on this? This allows you to basically use that function without having to define like expansion general for u, expansion general for q, which I saw a lot of people doing.
How do you generate the subscripts for var n?
You would type var, control hyphen, and then you move to the right, and then you're there. Is that what you meant?
Yeah, thank you.
Yep. Why am I making u sub n and q sub n a symbol? Yeah, great question. So what is the deal with this stuff here? I only have half an answer for you. And my half an answer is, by default, Mathematica doesn't think of u sub n the way we think of u sub n. We're used to thinking of u sub n as if I give you an n of 2, it makes it u of 2. Mathematica won't do that by default, and you'll have problems if you ask it to like replace u of 3 with this thing, because it'll say, oh, I don't have a variable u of 3. And so this basically makes it treat subscripts the way you and I think of subscripts. The reason why I say it's half an answer is because I don't know the way Mathematica treats subscripts by default. But I know that it won't work, and I wanted to keep the notation. We don't have to do it this way. I just wanted to keep the notation in our Mathematica notebook looking as close to what we did in class as possible. Let's see. Someone repeat how to get the subscript. Yeah, sure. So how to get the subscript is type what you want. So we'll call it x, control hyphen. The hyphen is the one between the u and the equal sign, and then type. And just in case it's important, to get the superscript, you go control 6, which is the one with the little caret, and that gives you a superscript. And you can square things or put it to exponential power, whatever you want. So in here we have it to n. So we did like escape e, escape makes an epsilon, control 6 makes an exponent, and we put an n up there, and we're good.
Can you scroll up?
Yep.
Professor Holmes,
Yes.
I have a quick question. So sometimes when you're like writing variables, you do like q of t or u of t or like bar n of t, but then sometimes you just write like u and q. Like how do we know like when we had to write like of t versus just like the variable?
Sure. I assume you're referring to here, right? Where I just wrote u instead of u of t.
Yeah, and you also did it earlier when you did the like line in 13.
Yes. Yeah, okay, cool. These require two different answers. This one's simpler. The reason why it's u here is because I defined it here as like variable subscript of t. And so I think I could, I'm not sure if I could. So I basically am saying whatever variable you want, whatever variable you send me, I'm going to make it a function of time. So that's what this notation is saying here. So it's kind of saying, send me a variable, and it'll be a function of time. So the reason why I did that is because all the dependent variables in our problem are functions of time. So you can just say, send it u, now it's u sub n is a function of time. Send it q, now it's q sub n is a function of time. So that's just because u is the dependent variable. And the way we define this function, whatever dependent variable you send it, is a function of time. I could have made this a function of something else. And I also could have made it even more general and said, I'm going to like independent variable. And I could send this to be independent. I'm just making this up. And then I could make it so that my variable is a function of space. So I could say that I could say that like u is take it to the second order is a function of x, and then I could replace this with u, replace this with 2, and replace this with x, and it gives me an expansion of u to different orders in epsilon, but now u would be a function of x. And so that was just for simplicity, since all the variables are a function of time. This one's a trickier question to answer. And in order to answer it, I'll bring you back to the way you would solve this for if we wanted to solve it analytically, which we would not need to tell it epsilon. So the notation for doing that would look a little bit like this. However, the d-solve, which is solving this equation analytically, is trying to solve for u of t and q of t for all time. So the reason why you put this kind of u of t, q of t here, where the square brackets are with time here, is because you're asking it to solve over the entire domain of time. So this would be the notation for that. So when we use ND-solve, we're basically telling it, I want you to solve for the dependent variables u and t, but you can't solve this problem for all time because that's not how a numerical solver works. You can only solve it for a specific bounds on your time. So I'm going to say solve for u and q over this time domain. So it's a little bit more of a subtle reason there. Oh, this is about to crash because it does not want to solve this analytical equation. Abort. So that's the reason why we have to do this numerically. Does that help? I know it's a little tricky and they're both different reasons. This one's a little bit more kind of mathematical and this one's a little bit more stylistic. Does that make sense?
Yeah. Yeah, that makes sense.
Okay. Okay. Should we try to solve this equation? So these are the solutions. Remember, I keep repeating this because I think this can be a point of confusion. These are the solutions. We just need to figure out the coefficients. In addition, we also, in order to solve this problem and any problem that we're using a perturbation method for, we need the ability to examine our equation to specific orders in epsilon. We have to start by evaluating our equation to order 1, then move on to evaluating it to order epsilon, epsilon squared, epsilon cubed. The reason why I'm bringing this up is because if you look at our equation, it's not at all clear what that equation looks like to order epsilon, or to order epsilon squared. Epsilon appears in this exponential function. That's a pain. And so what we're going to end up doing is expanding our equations using a Taylor series expansion, inserting our solution, and then truncating it to whatever order we want. And that's always the procedure. We take our analytical expression, we expand it using a Taylor series expansion, we insert our guesses at the solution, and then we truncate to whatever order we want. We always start with order 1, and then we move on from there. So let me expand order 1 and see what I'm saying, and kind of go through what I'm talking about. So I'm going to define 4 new equations. We had 4 to start. I'm going to do 4 new equations. These are my order 1 equations. I'm going to unpack what I wrote here so that it becomes clear. So EQU is what? It's this thing. That's the equation we want to solve. But I would like to replace u of t with my expansion for u. And I'm going to replace it with my expansion for u to order 0, which means it's going to just use this variable here. And we can see what that looks like. All it did, I'll delete it, is it's going to take this term and turn it to u sub naught of t. We also have to replace q of t, so we can do that again. Oops. And this time I'm going to do q of t. My variable is now q. And you can see that it replaced this thing with q naught of t. After last class, I went into like the Mathematica forums to figure out why it doesn't replace derivatives automatically, and just ended up with a bunch of people yelling at each other. And so I still don't know the answer. And so we're going to have to manually replace the derivative as well, which looks like this. And now we have our differential equation where we've substituted in our solution. And that's all. And I stored that as my new equation here. So I'm going to delete this because these 2 lines are identical. And I just stored that as my equation 1 for U, equation 1 for Q, and this is what they look like. And you'll notice we accomplished one of the two goals. One, we substituted our guesses for the solution into there. The second goal we have to do is expand this solution so that we can figure out what's happening at order epsilon squared, order epsilon cubed. The order of those things doesn't matter. You could have expanded the equation first and then inserted. I did it this way just arbitrarily. So the expansion looks like this. It says take my new equation. So I'm going to run these. Take my new equation, do a series expansion. We're going to start with order 1 solutions, which in Mathematica, that means do a series expansion of epsilon around 0 to the 0th order. So let's see what that looks like. Looks like this. And we want to get rid of this pesky order epsilon to the 1 power, so we go normal. Make that equation look more normal. And then we get a very simple equation to handle. And we do that for all of them. So we do that for the 2 equations. We could do it for the initial conditions, but there's no epsilon in the initial conditions, so there's no reason to do an expansion about the initial conditions. It's not going to be able to, it's not going to change them at all. And so then these equations here, when I'm looking at the linear version of these equations, in which we remove the nonlinearity that occurs due to the presence of epsilon, reduce to these 2 equations down here. And let me pause to take questions. Yep.
So I am surprised that I didn't really think about this, but going back to the debate of plugging in the derivative, basically, and I think I plugged in the derivatives for the later equations, but if you define your equation with the, an equation of U underscore T, that whole thing, I just plugged in expansion general U and expansion general Q, and I believe that replaced the derivatives.
Oh, okay. Well, you'll have to show me that code later. Yeah, I would be interested to see that, because I thought I tried that before, but yeah.
I think I did it. Like I plugged in the derivatives later on, but yeah, president.
Yeah, if you find a way to do this without me having to replace the derivatives, please send me your Mathematica file, because it annoys me to no end. So it's just a lot of extra code that seems completely unnecessary. So yeah, please do share. Questions on how we've gotten here? Are you able to get here in your Mathematica notebook? I know I'm going maybe fast, I'm not sure, but please let me know.
Based on how you had defined the general equations last time, it looked like you kind of brought everything to one side and set it equal to 0. So that like on the differential equation side, so that's how I had set mine up this past week. I guess, is there an issue with doing it one way or the other, or will then like the, I guess, notation of how you solve it later become an issue?
Nope, and that's I think what Reese was asking here in class earlier. It was like, why did I do it a different way? And it was mainly to show that there is not necessarily a right or wrong way to do it. It's kind of, each of them has their like notation differences that you may or may not like. And so if you did this the same way as we did the perturbation problem on the projectile, it should absolutely work out the same. Your notation will look a little bit different than mine, but you can absolutely do it that way, and there's no reason not to. I am aware that that notation kind of scares off new Mathematica users. And so I was going through this notebook with a slightly different approach to defining the equations, just to make it perhaps more straightforward. So, but there's no reason, there's nothing like mathematically or coding wise that would make one way work or not work based on the 2 ways that we've talked about it. So it's mainly for just kind of showing there's different ways to code up your solution. But yeah, you can absolutely do it that other way. That's completely fine.
I had a question on line 35. You say equation U1A, and it's like a normal series, and you're setting epsilon between the bounds of 0 and 0. What step is that conceptually?
Sure. So don't think of it that way. Think of that as read this sentence like this. I don't want to do this. Let me do a text line. This should be Taylor series expansion of the variable epsilon about epsilon equals 0 to 0th order. So that's series is this. You're doing a series of, sorry, let me actually make this even more clear. Taylor series expansion of our equation for the variable epsilon about epsilon is equal to 0 to the 0th order. So that's what this notation is saying. If you're ever, so this is saying, do the series of our equation to the variable epsilon about epsilon is equal to 0 to 0th order. So now let's just do this about epsilon, say is 1. Actually, I'm not going to do it here because I don't want to redefine stuff. Let me pull it out. Let's just see what happens. I change this to 1. And look, it's this is the part where you can kind of see what's happening. That replaces in your equation this. You go back to doing like Taylor series expansions and multivariate calculus. You're doing like f of x minus the like a usually, right? F of x minus a, where a is the point where you're taking the expansion around, and then you're telling it to take it to which order. And I can go to second order. Second order gets really complicated because it's got 0th order, 1st order, 2nd order, and then order cubed. I can go about a, and now you can see it's epsilon minus a squared, epsilon minus a. And so that's what this notation means. And fear not if you're like, how would I remember that? Just, you can literally just click, oops, mouse over it, and I had it. Hopefully you can see that on your screen. It says generates a power series expansion for f about the point f equals x naught to order x minus x naught to the n, which is probably a cleaner way of writing a sentence I wrote. Does that help?
Yeah, that makes sense. Thank you.
You can do this for all the functions in Mathematica. Just literally mouse over it. There should be a little double caret. If that's not enough, you can do that and go here, and I think that takes you to a help file where it shows you examples on how to use it.
That was slightly kind of a bit question.
Yeah.
Did you not run the line where you define the expansion general as a function?
Oh, hold on, I have to delete that. I changed this. No, I ran that. Sorry, it's right here. Expansion general of variable that.
Okay.
It's slightly different than the last one, and that was just
that's an epsilon to the end, right?
this is epsilon to the n, yeah. All it's doing is doing a summation of our variables, subscript n. Our variable is a function of time, so we just send it that, times epsilon to the n. So it's just doing a power series. Okay. Other questions? At this point, our procedure is the same and it's repetitive now. We substituted in our expansion, we truncated our series to the order that we're interested in. We always start with order 1, and then we move on to the next highest order in epsilon. So we inserted our expansion for U, inserted our expansion for Q into the equations and the initial conditions. We truncated our series by taking, this is mathematically equivalent to taking epsilon to 0. So you'll notice there is no epsilon in our equations, which is why this is the order 1 solution. And all we have to do now is solve this. And remember, this is going to use our DSolve notation. So we're solving differential equations. So I come here. I was talking to someone maybe last class or last office hours. What I like to do is before I define something as a variable, I run the code and make sure it works. So for instance, this is the DSolve equation. I want to solve this system of 4 equations. Now my 4 equations are my 2 approximate equations here and my 2 initial conditions. And remember, we didn't have to do anything, the initial conditions, because these things here are doing an expansion about epsilon, and our initial conditions don't contain epsilon, so that doesn't change anything. So I have 4 equations. Now my 2 dependent variables I'm solving for are not u and q, but they're u naught and q naught, and I'm solving them for all of time. They're both functions of time, and I'm solving them for the independent variable t. And I run that, and I'm going to get a list of solutions. The first solution is for q naught. Second solution is for u naught. So if I want to pull out the first solution, I type in square bracket 1. That actually just removes the outside parentheses. So look here. Why it needs 2 sets of parentheses is, I don't know, but it does, I guess. So you can see that there's 2 here. So putting square 1 just gets rid of the first one. And then I can, just like MATLAB, I can say give me the first solution. That's the q naught. Or I can say give me the second solution. That's the u naught. And so then all I did was I said, well, I want to replace the first solution, which is q naught, with what I have there. Oops, why doesn't that work?
The t.
Exactly, t, thank you. It would also give you an error if I said replace the first solution with u naught, because there is no u naught for the first solution. The first solution is for q naught, so it doesn't work. So if you mess up, it'll tell you. So I took the first solution, which is q naught of t, and I get this exponential term. And I just stored that as my order 1 solution for q. And I did the same thing. These 2 lines of code are exactly identical, except for the first one calls the first solution, the second one calls the second solution. And the first one has q, and the second one has u. And I solved it for order 1 for q and order 1 for u. Take a second and see if you can get that to work for u. Not the variable u, just you yourself. My next step is a little, seems a bit foolish or unnecessary, but I think it's important because if you forget this step, you'll mess up the solutions at higher orders. So I'm just kind of doing it to be, I don't know, super detailed, I guess, because if you forget it later, it'll be a problem. And the point I want to make here is that this is not the solution. The solution to our problem, for instance, let's look at q. So I can go expansion general for q out to order 2. The solution to our problem for q is q naught of t plus epsilon q1 of t plus epsilon squared q2 of t. What we solve for is q naught of t. So what I'd really like to do to be careful with our math is to take our solution and then insert for q naught my order 1 q. Oops, I forgot to tell it what I'm doing. I'm sending q naught of t to be order 1 of q. Now we're only doing this out to first order, so I shouldn't really have these second terms because I don't know what the coefficients are, so I actually should change this 2 to a 0. And you'll notice that this output is the same as this one, because at order 1, epsilon doesn't appear. But if you don't do this later, you're going to think, oh, I have the solution. You're going to plot it. It's going to look nothing right at all, because what you're solving for at each order are the coefficients that then need to be put back into the general solution and multiplied by epsilon. It's a subtle point. It probably doesn't make much sense right now, but in the next order, it'll make more sense. So that's what I'm doing here. So that's why it's that's why I do this whole thing where I introduce my solution at order 1 and my solution at order 1 for Q and U. Even though they give you the exact same output, it's mainly just so that way, if we repeat this procedure going forward, we don't skip this step. And then we can plot it. So to plot it, I'm just going to store my plot as a variable, and I'm going to plot my solution at order 1, my solution at order 1 for Q and for U. Over the same time domain, I'm going to plot it dotted and label a bunch of stuff. And then I can show my plot with my numerical solution. And this just kind of reinforces what we started out talking about. We said that for this particular problem, kind of linearizing it and solving it when epsilon is equal to 0, you still captured the dynamics at early time and at late time. It starts at 0, increases quickly, plateaus at 1. What you lose is the intermediate nonlinearity, that factor where it's going to kind of oscillate, over damp, and come back to a value of 1. So at our linear order, we lose all that nonlinearity in between there. We just kind of get this curve that bends towards 1 and bends towards 1. It clearly works at long time, it clearly works at short time, but this is a problem where you might be interested in what's happening at the intermediate time. Maybe you don't want to have an epsilon where this peak here exceeds a certain value. What value does that peak exceed? That might be something that's relevant to your problem, and it might be a design criteria. For instance, in a lot of like electrical engineering, where you're trying to look at kind of the feedback control and the signal control, signal processing. So it works over here, and it works over here, and it really doesn't work over here. So we have to go to the next highest order. Before I do that, let me take some questions on the order 1 solution. Should I move on? Everything we're about to do is just a repeat of what we just did, except we have to replace U naught and Q naught into our next set of equations. So it's really the same procedure. Take my initial equation, do my expansion to whatever order I want, replace U, Q, and its derivatives, do the same for the initial conditions, expand the series and truncate it to whatever order I want, in this case, the 0th order, solve it at this order, insert it back into the general solution that we guessed at, plot it. We're going to do the same thing. So now we'll go to order epsilon. Okay, I tried to make this easier to read. You'll have to be the judge on whether or not it's actually easier to read. So I'm taking my equation U, which is the initial equation that I wrote down, and I'm going to replace it. And I just made each line its own replacement rule, so that way it's easier to see. The only thing that's tricky here, I don't know why, but you have to keep the slash dot on the preceding line. So after slash dot, you can hit enter. So it goes EQU slash dot, and then I typed in my first replacement rule. This should make sense. Expansion general for U up to order 1, expansion general for Q up to order 1. My derivatives, that's fine. So these first three are kind of standard. And this is what we did last time. We just had zeros in there. But now we also have to tell it that we know U naught and we know Q naught. And not only that, but we also know U naught prime. And in the next one, we'll know Q naught prime. So we take order 1 is our, order 1 for U is U naught. So we replace U naught of T with order 1. We replace U naught prime of T with the derivative of U naught of order 1 with respect to T. And we replace Q naught of T with our order 1 solution for Q. Yeah, good question about equality. One equal sign, hold on, let me make sure I'm on a new line here. Let's do it up here. So the question in the chat box for those in the class was, what's the difference between equals, double equals, and colon equals? Okay. Single equals, oh gosh, don't do that. So A equals B. You should read this as like assign B to A. So earlier right now, I'm assigning the result of all of this to this little variable here. The easiest way for me to remember this is that I can assign this output of a plot to a variable. So that way I can just kind of call numplot. I can say like, hey, show me numplot. And that instead of having to type in all of this, I just assigned all of this to a variable. So it's kind of like just shorthand, taking all this and solving this numplot, and then I can plot that. So the single equal sign is like making a assignment of some number or some output or some calculation to a variable. Double equal sign is equality. How do I want to write this? A is equal is kind of killing the point. There is equality.
Used when defining an expression.
Yeah, expression, I guess, is a better way to think of it. A and B.
Whereas the single equal is defining a term.
Or, yeah. Oops, I have to be over here. Oh, gosh. Used for an expression, a mathematical expression. And the way I'm writing here with the parentheses and the stars, these are comments. These are like inline comments. A is a function of x, x squared, is how do I want to say this? It's kind of like assign the left-hand side to the right-hand side, but don't evaluate this expression.
Or define a function with inputs.
Yeah, this is defining a function with inputs, but you could define it with either this is fine or also, hold on. This is fine. This one, I think, assigns and evaluates.
Can you?
Why do you care about this? I think is a reasonable question. Oh, is that?
Can you plug stuff back in later? So like, can you, after doing that line A x underline is equal to x squared, can you then go back?
I'm not sure. I'd have to check. Maybe not.
C.
I'm not sure. I guess we can try. I don't want to run the top one because I don't want to lose Let me just see if this is actually right. So if I do a of x, yeah, it worked. So now if I do a of 2, yeah, okay. So how I wrote it is right. This is like safer if you're defining a function. And the reason why I say it's safer is because there are some functions that you don't realize you can't evaluate them immediately. The most obvious one is the one we've already defined, which is, where did it go? Which is this one. You cannot run this one immediately because you're asking Mathematica to give you a summation of your variable from n is equal to 0 to nn. It doesn't know what nn is, so it do this indefinitely. This is kind of like having like a, what do they call those when you're coding and you have like a for loop that just runs forever. Like that's what the output of this would be because it doesn't know what nn is, so it's going to go from 0 by powers of 1 to an unknown thing, and so it can't do that. So by doing this, you're saying, hey, store this, but don't run it until I actually give you some numbers to stick in there for nn, because otherwise you're gonna just run forever and it's never gonna work. This happens a lot, especially with like parametric functions and solving things numerically, where you might, kind of hard to give a clear example, but this happens a lot where it'll sometimes yell at you because it's basically saying like, I can't run this thing because I don't know how to put a value in, and I need a value to do this calculation, and then it'll just kind of yell at you. So this basically says like, hey, just save this until I tell you an actual thing for var and nn, and this usually has to actually be a number. Does that help? In general, I never use this one because I'm always assuming that I probably better safe than sorry and can just say you can wait. There's usually not really much of an advantage to having it evaluated immediately when you define it. So I always just do this, just in case. But this can work, but for this one, it definitely wouldn't work. And there's other examples where it definitely wouldn't work as well. Does that help with the equalities? Sweet. Okay. Hopefully that gave everyone some time to start maybe typing in these things, and then hopefully doing the same for equation Q. It should make sense, I hope. Seeing them line by line and recognizing that you have to, oh, I didn't put an answer down here. Seeing them line by line and recognizing that all we're doing is, these first 3 ones are doing our expansion. So we're taking the original equation and expanding it. And then we're taking that expanded, we're taking that original equation and we're inserting our solution. That's what we're doing. Insert our solution for u. So this is going to replace u with some stuff that has u naught and u1. Replace q with q naught and q1. Replace our derivatives with with q naught and q1. And then we actually know u naught and q naught, so we're replacing those. And then we replace our initial conditions with our general solution. We had to do one extra thing here, which was take time is equal to 0. But that's just because it replaces this with u naught of t, and we need to tell it that it's u naught of t, but t is actually 0 for our initial conditions. If it was the initial conditions was t was infinity, we'd use infinity here, or so on. Same step. Insert our guess, and then insert what we saw in the last order. Yep.
Yeah, so I'm just noticing, I think that, for example, for E, Q, U, epsilon at the top there, you know, like for example, there's not a Q naught in that equation.
What do you mean by that?
Like,
there should be a Q naught in that equation.
well,
because look, if I go up here, so that was E, which one was that I had highlighted? EQU. EQU has a Q in it,
okay.
which means it will have a Q naught and a Q1 and a Q whatever, which is why in here we replaced If you leave it out, you can see what happens.
Yeah, I was about to say, oh, never mind. Wait, can you scroll?
Which way do you want me to scroll?
Right, yeah, right here's perfect. Oh, never mind. Okay, I was just wondering if basically if you could ever try to replace something that wasn't there and like if it would yell at you or something like that. So for example, if you try to replace,
Yeah, we can try that. We could say like, let's see here. Let me do one. We could do like,
because I just think of an example where I'm like, do I want to like go back and check to see what's in the equation, or do I just like replace everything?
yeah, like this comes up a lot in like dealing with matrices and like sparse matrices, where you just kind of like replace everything, and then you just don't even worry about it. Like it makes for faster computations, even though you think like it's wasting time, but you can. I think it's fine. So let's just check. So I could do like r squared minus 4r, replace t with 3, replace, so this shouldn't do anything.
Right. Yeah.
And it doesn't do anything. So and it also doesn't yell at you, which is like the more important thing that you were asking. So it doesn't do anything and it doesn't hurt. So you can, can replace with, I guess what you're getting at is, I could also take this thing here and replace with q naught prime, which does not appear, and it would be fine. And the reason you would do that is because you have 4 variables, u naught, q naught, u naught prime, q naught prime, so you just replace with each one at each step, and that would be fine.
And then you could basically have the same replacement for both the first equation and the second equation.
Yes, exactly. Yep. So these look awful, right? Like this looks like a nightmare. But we are not done, because now we have to tell it to truncate this equation and this equation at order epsilon. And we just do the same thing we did before. This is the exact same code, just changing it from 0 to a 1. I'm getting a syntax error. Uh-oh. So q naught cannot be followed by t. Well, that's an interesting one. So this should be able to be followed by t. I don't know. I'm happy to troubleshoot that syntax error, but I would have to jump onto your screen for a minute. So why don't we, I don't know the way to do that easily. Maybe if we have time for a little break, I can jump on and see what happened. I'm not sure why it's yelling at you to do that. My guess would be, okay, maybe this could be a solution. It's important for me to tell, this could be helpful to everyone though. It's important to know that the order of operations here matters. Because if you try to insert u naught of t and q naught of t into EQ capital Q, before you do these 3 things, there is no u naught of t and q naught of t in that initial equation, and so it's not going to do anything. And then you're going to be left, and you're going to still have those things in your equation. So you have to first. So remember these things. This is inserting u naught plus epsilon u1 plus L dot, and then this one is doing the same, but for Q. That made things look ugly. Oh well. And so you can't insert something for Q naught and U naught if you haven't actually already inserted those things that have U naught and U of T equals this T, this of T. So it could be an order of operations issue that you're getting that syntax error.
I'm wondering also if it has to do with the fact that my EQU epsilon is in black font, but then EQ Q epsilon and then IC U epsilon and IC Q epsilon are all blue. So it might be something that I did that is just making the next 30 lines after EQ U epsilon not behave well.
So just so everyone knows, blue variables means they're free. They've never been used. They've never been defined. They have nothing stored in them. So here I haven't evaluated this cell yet. And so EQUE is black because I already ran this one. But EQU epsilon A is blue because I haven't ran that code yet. So it doesn't know what that is. As soon as I run this code, it turns black because now I've stored some information there. So it could be that maybe there's a cell you didn't evaluate that would lead to you trying to insert something that it doesn't have a definition for. I will try to jump on and help if I can with that. In the meantime, I will say, let's see. Oh, this is the same here. I'm just truncating my series out to order epsilon. I'm solving. Hopefully this all works. Yes, it does. It looks really awful, but that's okay. Be thankful that we didn't have to do this out by hand. And remember, this is the key step in the last problem. This is just Q1 and U1. And we have to remember that our actual solution is this, Q naught of T plus epsilon Q1 of T. This is just Q1. If you plot this, you're going to get something that's interesting, but not at all what you want. The reason why it's interesting is it's kind of telling you, like, you know how with like a Fourier series, you end up with like a summation of sines where you have like different waves to kind of construct a solution. This is basically saying, like, add this small correction to your initial, add this small correction to my initial solution, but multiply that small correction by my small parameter epsilon and add that to my leading order linear solution, which is this thing. So in order to actually compare our order epsilon solution, we have to take Q1 and insert it into this equation, which contains epsilon and Q naught. And that's exactly what our next line of code does. We did this in our last step, but it ended up resulting in just showing us this. But now at order epsilon, we have our order 1 solution, which I've highlighted in blue, and our order epsilon solution, which I've now highlighted in blue. And now you can see that our order epsilon solution contains what we just found, multiplied by epsilon, added to our leading order solution. So we can run that. And now we can plot these. And I plotted these with a dash, and I can see that now my leading order solution went like this. If I follow that curve and I look at the dash solution, now I'm doing a lot better for my approximation to this problem. I've almost perfectly captured the dynamics. I've certainly got some of the nonlinearity here between 1 and 4 in my dimensionless time. And I've gotten a lot better in my blue curves as well. For fun, I did this up to epsilon squared, just to show you that it does in fact get us to the solution. The procedure is exactly the same, it's just you have a lot more substitutions to make. So I'm doing this to epsilon squared, and I have to do the same exact stuff, but now I'm replacing this with 2's. I have to replace all my U naughts and Q naughts, and then I have to replace all my U1s and Q1s. Same thing, replace it with my guess, so up to order 2. Replace all my U naughts and Q naughts, replace all my U1s and Q1s. I have a really, truly horrendous equation here, but that's not a problem, because that's why we're using Mathematica. I can truncate this thing. I can, oops, I don't need this. I can solve for my two Q2 and U2, and I can insert these in. You end up with something that's really awful, but the reason I'm doing this is just to confirm what you would probably suspect, which is if I plot this now, I can see this line here, which is a dash dot, really sitting on, I'm going to make this huge so you can see it, everyone can see it, because I didn't let you have time to do this along. Now you can really see that my order epsilon squared solution is really capturing this thing quite well. Maybe not perfectly, you can compare and decide to yourself how far to go. But the point is, and I will share this thing on my website so you can check it out, this procedure is really like, you know, you're just repeating the same thing. Insert your guess into the equation. Insert anything you know about the prefactors for that guess. So the prefactors being variable sub naught, variable sub 1, variable sub 2. Then take that new equation that has your guess or your solution and expand it and truncate that series to whichever order you need, and then solve the differential equation for the only unknown parameters. Insert all that back in to your guess for your solution and plot. And that's the procedure over and over again. And it works. Like I mean, this looks awful, but like if you're doing this, there's a couple things to give you a peace of mind. One, if you mess up, even if you don't know the numerical solution, say you have no idea what the actual solution is. Intuitively, what I want you to get a feel for is that as I increase my order to my approximation, this curve is changing. It changes really quickly from order 1 to order epsilon. It changes a little bit less from order epsilon to order epsilon squared. It's going to change a little bit less from epsilon squared to epsilon cubed. If what you're plotting for your approximations doesn't follow that trend, that's a good sign that you did something wrong. It should really just be adding a smaller correction to your approximation. So even if you don't have a way to solve your equation numerically, you can still get a feeling. You're kind of looking for some convergence. Like you're looking for this curve to kind of approach some curve. And each time it gets a little bit closer, but it's maybe not exactly right. So you can go to a higher order term. So you don't need to have a numerical solution to kind of tell you if you're doing this right or wrong. A lot of times you can't really easily get one. But there are still ways that these approximate methods can be verified. And so hopefully like understanding how the approximation is going to kind of slowly get you closer there. That's the way to think about to kind of check yourself. All right, I raced through that last part. Let me take some questions. Hold on one second. I'm going to grab this one in the chat just to make sure I didn't miss something. What does the arrow do again? Yes. Yeah, sure. What does the arrow do? Or does that make it easier to see? I think this might be easier to, yeah. So slash dot is replace all. So this is kind of replace all, and you give it a rule. And the way Mathematica deals with rules is with the arrow. So this is shorthand for replace all. You could, if you wanted, instead of using this notation, you could type out replace all, I think. Yeah, here. Replace all x, and then you just give it a rule. So you're saying replace all x, the rule is x goes to a. And so the arrow is kind of the rule, and the slash dot is replace all. Here I have slash dot, and I moved it to a different line, but this really kind of goes here. So it's replace all u of t, and the rule is that u of t goes to, is replaced with this junk here. I think maybe what you're referring to is here, where I don't have the arrow, but I will remind you that if I run this code, everything after here, look what happens. the arrow is there. Q1 of t is there. So I'm kind of the rule is this. This is where, like, I don't know. This is where Mathematica is tricky because it's like a different way of coding. It deals with everything with lists and rules, and so when it gives you a solution, it's just giving you a list of rules, which I don't know why. But this is, so the solution to this differential equation is a rule that if you replace Q1 of t with this thing, that will solve these differential equations. And so here we didn't need the arrow, only because the arrow was part of what Mathematica spits out for the solution. There's a question in here, I think.
In the visualizations of the graphs, as we go increase order epsilon or something, the solution sort of approaches the numerical solution, or what we assume to be the ground truth. Is there some way to analytically describe the difference between each order? Or is
Yeah, and so these are, I don't think I've said this. This is a good question. I don't think I've said this. But let me see if I can open our regular perturbation intro. So you should have this notebook, I think. I didn't say this last part here. These approximations, these approximate solutions are asymptotic solutions to our problem. And that has a formal mathematical meaning, which is that if you take the difference of x, for instance, and our asymptotic solution for x at a given order, and divide that by epsilon to that order, take the limit as epsilon goes to 0, this gives you a mathematical way to quantify. So this is what I mean visually. So if I take my solution and then I minus the order epsilon solution divided by epsilon to the order that I solved it, and I take the limit of that as epsilon goes to 0, that is the kind of mathematical way you can verify that you have an asymptotic solution. For everyone else listening, I didn't go through this because, well, I mean, this is a lame answer, but we're more maybe engineer physics focused than we are mathematical. And so there are questions and interesting questions about, like, do these series have to converge for them to be asymptotic expansions? The answer is no. That's actually a little bit nuanced and subtle. This approach of kind of taking the limit of your solution minus the what you found at that order for your solution over epsilon to the order as epsilon goes to 0 is the formal way that you can just kind of verify that you have an asymptotic expansion, which is what all we're doing right now. We're asymptotic expansions, asymptotic solutions. So yes, there's a formal way. It's maybe a little bit beyond where I want to get into the weeds for us here, but
it's
yeah.
just general. But from that engineering perspective, then, if the stuff we're doing is asymptotic, doesn't that imply that there's a approximate closed form or approximate analytical solution? I think
No, I think it implies that there is a solution.
Yeah.
But it doesn't imply that it's closed form or analytical. It just implies, so it implies that there is a solution at that order that we, but it doesn't imply that there is a solution at all orders. And again, I would point you back to the projectile problem. We have, at each order, we have this asymptotic solution until we have no solution at all. And there's nothing at each order that will ever tell you that we're going to lose a solution. So And that's why we don't have a closed form analytical solution for all epsilon, because for each order of epsilon, we have a solution that we can kind of verify, but we know nothing about the next order.
I had a question about the Taylor expansion for epsilon. So I remember in like the order 1 solution or the order 0 solution, we have a Taylor expansion for epsilon, but we don't do that. We don't expand it further in the subsequent like steps, the subsequent orders, right?
Let me see if I can. So at each thing we say, there's kind of 2 expansions that happen. And so I want to make sure we're aware of that. One is we have to assume a solution for U and assume a solution for Q. And we assume that solution is going to look like a power series expansion for U up to whatever order epsilon we're interested in. In this case, we're interested in order epsilon 1. So we stopped at order epsilon 1. We could, at the next order, we did epsilon 2. This is the first expansion that we use. This is like a power series expansion that we use as our guess at the solution that we're going to insert into our original equation. But the problem is so now we've inserted this into our original equation, but look what happens. I insert this into our original equation, and I end up with this. So this here, this thing I just highlighted in blue, is the result of running this code. So sure, I have terms that appear order epsilon. This is my order 1 solution. This is my order 1 solution. Sorry, this is my order 1 solution. This is my order 1 solution. But then I also have this complex term here, which has an epsilon that appeared in the original equation. Because remember, this power series expansion, we're kind of inserting an epsilon into U, right? That's exactly what we're saying here. I'm going to run this again just for clarity. We're saying that U can be replaced with a power series expansion that goes with U0 plus epsilon U1. So we're kind of adding an epsilon into our approximate solution for U. However, there's already an epsilon in this equation. How do we handle this? Well, the way we handle this is we take this output here, and we say, okay, even though I inserted this expansion up to order 1 and epsilon, there was already an epsilon in my equation, and I have to make sure that my entire equation is only containing terms of order 1 and order epsilon. So the way I do that is I take this whole thing here, and I do a Taylor series expansion of this whole thing. So I save this whole thing as this variable. I assigned it to EQU epsilon. And so I say do a series expansion of this whole thing about epsilon at epsilon naught of 0 up to order 1. And the result of that is it takes this equation and simplifies it to this equation. Now you can see very clearly, well maybe not very clearly, but maybe a little bit clearly, that the only way epsilon enters this equation is order 1. Epsilon, those are the only way it appears. It's up to order 1. Whereas if I go back to my original equation, I have an epsilon here multiplying an epsilon here within an exponential. So going from here, which is not, this contains terms of higher order epsilon. This contains terms only order epsilon 1, which is what we need to be able to solve for our coefficients at order 1, or order epsilon to the 1. Does that help?
Yeah, that makes sense. Yeah.
Let me grab the chat because I think I saw something pop up in here. Ah, cool. All right. Syntax problem resolved. Woohoo! Other questions? From the Mathematica to the conceptual, how are we doing? Like I said, next class, we're going to move on to singular perturbations, and they rely on you having a good understanding of how to do this. And so My recommendation would be to go back and solve the projectile problem on your own from scratch, and to solve this problem on your own from scratch. And to pretend like maybe you don't know the numerical solution. What happens? Does your solution make sense? Or to kind of see what happens if you take the solution I've gotten here. If you perhaps don't want to start from scratch, you can certainly take what I've done here and literally just go out to epsilon cubed and see what happens. And how do you do that? Well, all we have to do at each order, at each order, remember, all you're doing are these 3 steps. You're taking your original equation, inserting our guess, and then inserting everything we know about the prefactors. Inserting our guess, everything we know about the prefactors. Your guess has to be of the appropriate order. At this point, we're of epsilon order squared. And then you're going to do that for the initial conditions. Then the next step is truncate your series at order epsilon squared. So you have to take what we just did here, this awful stuff, and truncate it. Solve the differential equation for the only 2 unknowns that remain. So if I look at this awful thing here, yes, it's really ugly, but if I'm careful when I inspect this, I see that really all that I don't know is U2, and I think there's a Q2 buried in here somewhere. Maybe. Here's Q2 prime, and so on. And then I'm solving for those 2 things, inserting them back into my guess. So again, this is the crucial part. Take my guess, insert my unknowns, Q0, Q1, Q2, U0, U1, U2, and then I plot. This is really like a copy and paste exercise to solve it out to order epsilon cubed. There's a lot that can go wrong in copying and pasting, but like you can start there, and then you can go back and do this from scratch, and then this should, and you can see what happens. Like, so for pretty clearly, you don't need to go to higher than order epsilon squared for the particular value of epsilon we chose. But look, let's just for fun, let's go back and let's solve our equation up for order epsilon 1. So I plot this. I'm going to change my plot bounds to 2, and so I have a much more nonlinear oscillation there. And then I'm going to change everything. I'm going to run all 3 of these, but I have to change one thing for each one, which is that when I plot it, I have to tell it to plot it. Well, that one doesn't matter. This one does. I have to tell it to plot with epsilon is 1. Why did that disappear? I have no idea. It's not great. I can come down here and I can tell it to plot for order epsilon. Why did my plot go away? I don't know. Well, I don't know what happened to my plot. I don't know why it's disappearing there. Maybe I could not show this thing.
Because the range is 0 to 1.2.
Ah, yes, thank you very much. Thank you. Ha, thank you. I should do that up here, 2. Yeah, there we go. So now I can clearly see that if epsilon's of order 1, it does okay, but not really. You know, it doesn't really capture the max, and it doesn't really capture the minimum at this next one. And so that motivates you to go to a higher order in your approximation. And so you can check for epsilon is of equal to 1. If I go out to epsilon cubed, is that adequate? Do I need to go out to epsilon to the 4th? And again, even if you didn't have the numerical solution, you could still be looking to see how are your curves converging as I take this out to higher and higher orders. Questions?
I guess I just have like two very general questions. My first question is, I guess like what is the main benefits of solving this with Mathematica versus like doing it by hand instead of like the plotting like benefit, like being able to check like your plot?
For me, it is my inability to do calculations like this that result in something that looks like that without messing up. And on top of that, having this kind of all, it would take me about 5 minutes of copying and pasting and double checking that I take each one to each order to do this expansion out to order epsilon cubed. Maybe 3 minutes. If I was doing this by hand, it would take me significantly longer. And then I would need to figure out some way of checking my answer. And like I said, even if you didn't have a numerical solution, I could check my answer by kind of seeing how it compares to my previous order solution. And so in a lot of ways, for me, it's, I guess, like, one, it's going to minimize my mistakes. Two, it makes it easier to kind of go to higher and higher orders without having to duplicate all my math. I just kind of can copy and paste and change one or two things. Three, I can visualize it. I guess the other thing is some of the stuff is not too bad to do by pen and paper, but like I don't remember how to do the Taylor series expansion of an exponential function off the top of my head. And so I'm going to have to go look that up somewhere. So my options are I go to Wikipedia, I go to my multivariate textbook, or I just come here and I say series exp of negative epsilon x for epsilon 0 to 3, and I have my series expansion immediately, which is something that like I don't remember how to do. And so it's kind of all of those things. And I guess the other thing I would say is, I don't know, I hope this doesn't come across as like intimidating, but like these are two of the simpler problems that you'll come across in how to do this. Like these are textbook problems. These are problems that got solved a long time ago. And so the problems you'll face in your research are probably ones that are not going to work out this nicely, especially at your first attempt, because maybe you're guessing what the function should look like, and maybe you're trying to you're not sure what your bounds are. You're not, like I think that as things get harder, you're having some tools at your disposal to help you kind of will only speed things up, kind of speed up your mistakes and speed up your recognition of your mistakes so you can go and correct your mistakes. Because never do I ever sit down for a research problem and just kind of code and then have a solution. It's always more of like, I do some stuff, it was all wrong. What was wrong? Oh, this part was right, this part was wrong. Okay, I changed it. Oh, actually, it turns out that the thing I thought was right was only right in this one limit. How did I know that? Well, I could plot, like I think it's important to remember that in research, you're just using different tools at different times to help answer different questions. And I think there's a lot to be said for kind of, I think we, in school, overemphasize the ability to do things on pen and paper. And don't do a good job of making it clear when it makes sense to use tools that'll help things, so you can spend your time on the interesting questions of your research and not the kind of, I don't want to say like not interesting mathematics, but like, you know, after doing this 100 times, like, I don't know, it's like, I'd rather spend my time thinking about the problem than correcting kind of my mathematical like errors that carried through. I don't know if that answers it. Yeah, like you can definitely do it by hand. It's going to be slower, like, and it might introduce large errors that you don't notice for a long time. So, you know, there's trade-offs there.
Yeah, thank you. It makes sense. I guess like also my second general question, this might just be like, I guess, preference. Why solve this like with Mathematica instead of like MATLAB?
Yeah, sure. Again, I kind of think of these as there being different tools to solve different problems. And MATLAB, it's helpful to think about what MATLAB was designed for and what Mathematica was designed for. So MATLAB is matrix laboratory. So its optimization it is designed to handle matrix operations faster than anything else. That's the goal. Is how do you do matrix multiplications? How do you do matrix divisions? How do you do things involving matrices where maybe I can pull in an image, and an image is a matrix that just has RGB values at each index, and MATLAB can handle all those things really well. So MATLAB is designed for matrices. Now, it doesn't mean it can't do things like this. However, if you play with Mathematica much, you know that the syntax, not the syntax, the way you have to input variables very quickly starts to look very different from what you might write down on your pen and paper. It starts to look really different than like the equation you're kind of seeing in the textbook. Plotting is not as kind of intuitive to it because you have to describe a space. You have to actually create a linear space over which you're going to kind of interpolate points to create your sine curve. Mathematica was designed for symbolic manipulation of mathematical expressions. And so things like plotting and solving and even just inputting and outputting equations, these look awful, but I mean, you know, like these look like the types of equations that you're gonna encounter in your notes in your book there. And so the equations look right, the manipulation of those equations look right, the plotting of those equations are straightforward, the way to do these series expansions where you're asking it to do a Taylor series expansion and truncating terms, it's all meant to kind of stay as close to how you would write and read math as possible. Whereas MATLAB, I think, as you get into the more complicated mathematical problems with MATLAB, you end up really far away from the mathematical equations you're solving. And I just think they're kind of different tools. Like you could absolutely like jerry-rig MATLAB to do this, but it'll be messier because you're kind of forcing it to do something it's not meant for. It's like you could use the back end of your screwdriver to hammer in a nail, but I mean, you could also use a hammer because it's kind of designed for that. And so like I would just say they're both tools that have fantastic strengths. The strengths overlap in some regions, but I would kind of, you know, try to identify what problem you're trying to solve and what tool is better for that problem. And so I think of MATLAB as just kind of having a different set of skills that is less useful for like applied math type problems and more useful for yeah, like matrix calculations, which, you know, a lot of things reduce to matrix calculations. If you're doing things, you can do a lot of finite element work in which you're basically solving these complex matrix equations. And MATLAB can be fantastic for that, maybe a little bit slow compared to higher order, lower level languages, but it really is kind of knowing what the tools are and being open to just having more than one tool at your disposal. I think the learning of these multiple tools will end up paying off, even if the learning curve is steep at first.
Thank you.
Other questions? I would encourage you to work through some of these things because on Tuesday, do we have class on Tuesday?
I think it's Monday scheduled because of the.
Oh, because of the holiday. Okay, cool. Okay, well, the next time we see each other, we will do a harder version of a perturbation problem involving what are referred to as singular perturbation problems, which you need to be able to do this for, and then we have to learn something new, which is trickier on top of it. So I would like you to all be confident with this beforehand. The homework I have for you contains both, I think, regular and singular perturbations. So I don't think I have anything to give you just yet because I wanted to kind of give you all the perturbation stuff, which may or may not be a good decision. But yeah, I would get comfortable with these regular perturbation problems. You can set up any initial value problem you want. You don't have to pick the two that we have, and you should be able to use this for. You should hopefully convince yourself if you take a nonlinear initial value problem, you should be able to use this to solve it. So I'll give you some on homework soon. But yeah, by next time we meet, we're going to look at a kind of a more complicated version of this. Yeah,
I was about to say, so when we are given the homework on that, I mean, can we just write Mathematica files, basically?
Yeah, for sure. I think, like, you know, the next time through that we go through homework, it'll most likely look like I'm going to share my Mathematica file and let me walk you through what I've done, and yeah, and that's good. Like that's what I want. I mean, like, I want yeah, I want this to be. I don't really need you to be proving to me that you can do this on pen and paper, because the number of problems that you can do on pen and paper are limited. Like they're just not going to be as interesting. Like you can't do more complicated things without them being incredibly tedious. Cool. Thanks, everyone. Have a good weekend.